Hey guys, it's Michael with Breaking Concepts, and today we're going to talk about equilibria of recursive sequence and CobWebbing. Now, if you guys are not familiar with the recursive sequence and, recursive discrete logistic growth model, I would highly encourage you guys to check out the previous videos within this series, which is called Recursive Sequence and its Applications. It's going to certainly be helpful, really help you build a better foundation with what we're going to discuss today. So today we're going to talk about both of the things. Before we get into cobwebbing or stable and unstable equilibrium, we would eventually have to go through an example that really help build our foundation and knowledge about what's going on with this chapter, and then we can move on to the next step. So without further ado, let's start by kicking off with what is an equilibria. So you guys can see an equation here, equal xt plus 1 equals to fxt. So we've seen this equation a lot of times. Now, equilibria, by definition, is a number x with what we call it an x hat. X hat that is left unchanged by the updating function. So we know the updating function basically gives you the value for next term by inputting the current term. So if you remember in our module function, right, we have an updating function. We input a current term, and we'll get the term for the future. So that's what an updating function does. Now in this case, our fx hat is actually equals to our x hat, which means the value of the input and the output is actually the same. Okay, so our xt is equals to our xt plus 1. The value is the same. Remember in our last video when we were talking about the discrete logistic growth model, what happens when our current population is approaching or equals to our carrying capacity. So right again, you see our nt is equals to k, that our k is going to be over k. So this is our discrete logistic growth model, and so 1 minus all this is actually equals to k over k, right? So we have 1 minus 1, but then we have 1 plus 0, which is going to be equals to just 1. So that's why we have nt plus 1 equals to nt, which is basically saying the future population is going to equals to our current population. And last time, I did highlight the fact that we're talking about equilibrium, which is exactly what we mean by today, and we're going to see more as we go in this video. So as you can see here, when our nt is equals to k, then our nt plus 1 is equals to our updating function, inputting the nt hat now, which is going to be equals to nt. So I hope equilibrium makes sense to you so far. Okay, so how do we actually find the equilibrium, our x hat? So step 1, we can actually solve for fx equals to x if possible. And step 2, we can also, for recursive sequence, we can also graph a y equals to fx curve and a y equal to x curve. So now what it means by y equals fx in recursive sequence is basically this one, right? Remember our updating function and everything is basically the y is our next term, right? Is our xt plus 1 is equals to our updating function inputting our current term, our xt. And so we want to graph the curve of y equals to fx, and we also want to graph the curve of y equal to x. Y equals to x basically means this one, right? xt plus 1 is equals to xt. So we have a straight line like this in the middle, which is y equals to x, or xt plus 1 equals to xt, this one. And then we want to find the intersections of these two curves, and that's how we get the value of our x hat. So we can have multiple equilibriums. So you see that we have 1, 2, and 3 equilibriums in total here. And just a super quick recap here. So remember that the updating function is also equals to our current term in addition to our difference function. So in this case, when ant plus 1 is equals to an, we got to make sure that the difference function is actually equals to 0, which basically makes super sense. So in order to make sure that our future term is equals to our current term, all we got to do is make sure that our current term does not have any, is not going to add anything, right? It's not going to go up, it's not going to go down, it's equal to 0, then the next term is going to stay the same. So an equilibrium point only occurs at values where the difference function gx is equals to 0. So absolutely, today we're going to talk about cobwebbing, we're going to talk about stable and unstable equilibrium. So before we can actually do that, I want us to really understand what the graph means. And I feel like really understanding the fundamental logic behind what the graph means when you guys are doing cobwebbing, the idea that you guys have, because of such a well-founded foundation, you guys are going to understand everything much clearer. and everything makes a lot more sense to you. So just pretty quick before our challenge, I'm going to do a quick introduction here. So if you see number 1 here is our recurrence web or Cobweb plot, which we have a y-axis of xt plus 1 and an x-axis of xt, which is the one that we're just talking about. Xt is basically our current term, and xt plus 1 is our future term. So the way we can interpret this graph is by inputting the xt, we would get the xt plus 1. Input current, you'll get future. Okay? And number 2, it is going to be our time series plot. Basically, t here represents time, right? And period. So let's say time could be day, right? Years, whatever. But let's say we say it's day. So for the time here, it's going to be start from 0. You can have 1, 2, 3, 4, 5, 6, 7, 8. But those numbers is going to represent days. So day 1, this happens, day 2, day 3, day 4. And we can see on the y-axis basically it says the population. xt is our current population. So in day 1, let's say here, day 1, what is the current population? What is the current population? Or in day 0, again, what is the current population? So this is basically the 2 most important graphs that we have to know. So for all xt that we see here, assume that it means population. Right? I know there's another thing called logistic map where the xt represents a fraction, but just for simplicity, here the xt represents the population, the number as a number. Okay, so I hope all that makes sense, and here's is actually the fun part. So we're going to do 3 adventures. We're going to go through 3 adventures that will eventually teach us what is a stable equilibrium, what is an unstable equilibrium, and what is cobwebbing. So first of all, in adventure 1, it says you start an experiment with 75 insects. So x naught is equals to 75. What happens day by day, right? So we get to start from day 0. We get to start from day 0. I actually forgot to make some notes, but just like our previous example, here and here we have 3 equilibrium, right? Point of contact. And this one obviously is going to be 0. This one is going to be actually 50, and this is going to be 100. And this is simply just for this example. We start an experiment with 75. So let's say 75 is here. So what this graph on the left-hand side tells me is if we input the current population, we would know what's the population for tomorrow. Right-hand side graph. Again, this graph tells us what is the current population at the current time period. So we know that, first of all, x naught is 0. So t0 is going to be 75. 75. Perfect. And now we can find what's going to happen tomorrow by going up on this graph. So 75 goes up, and we got something here. So here, we'll say it is somewhere around 85. Okay, 85. So the population for tomorrow, let's say 1, right? 1 is going to be 85 because we got this from the graph there, right? So this is day 0. That's what we know. Today is going to be 75, and tomorrow we're going to have. So now is day 1, and how do we start with the graph here? Well, we do know from yesterday that day 1, right, was going to be we're going to start with 85. So this time, as you can see here, 85 is already here. So this time, we can start to find what's going to happen on day 2. On day 2, we know that here now is 85. On day 2, we can go like somewhere here. Okay, and here, it will get somewhere around 95. So we know that day 2. Okay, so we know that day 2, and we presume that day 2 is going to be 95. 95. There you go. So we see that the graph is actually increasing. So day 2, we know that we start off with 95. So now we do a 95 here. We can go up, and then we can eventually go and find that it's going to be 99. By the way, this number, we're kind of making it up, but at the same time, it's kind of proportional to what we're looking for. So there is some truth to it. So now we know that on day 3, it is going to be, the population is going to be 99. And I hope it makes so much sense here. Right now, it's pretty easy. It's pretty intuitive. So now we're at day 3. So at day 3, we can start something like 99. Okay, and then we can come here, and it reaches maybe 100. So 100 is what we're going to get for day 4. Now, remember one very key thing. If you remember from our graph, that 100 is basically one of our equilibrium point. So what do you think is going to happen after day 4 Is it going to keep going up or is it keep going down? And the answer to this question is that we should be staying at the constant and leveling up at 100. Because again, day 4, we get an input of 100. And when we input 100, we're going to get 100 again. So in day 5, we have 100. And we're going to take this 100 again, come back here, go up, go 100 and 100 and 100. So we're going to keep in this loop. And here's the reason why we call this point an equilibrium point. Because it just stays there. So in day 7, the graph will look something like this. So as you can see in day 7, the entire graph is leveling off at 100. Just going back to this graph, right? So I hope this makes sense to you. So we're going to try a different adventure. What if we start from 120? So we know that this point is 100. And we can assume that maybe this point is 120. So what happens is the 120 would go here. But this time, the curve is here. And the answer would be 105. Let's say that. And let's say the next day we come again and we try to look for 105. So let's say this one is 105. 105 is kicking us to maybe 101. And the next day we're going to come and try to 101. So 101 is here. But this time the answer is going to be 100. So when we reach 100, we're going to stay at 100 because it's an equilibrium point. So the graph, we're going to look something like this. So from 120, we start at 120. There's 100. And we can start by, let's say, 1, 2, there's day 1, day 2, right? It goes something like this. And it just kind of plateaus from 3, 4, 5. So here's adventure 3. Let's say we start something at around 20. Tomorrow's population is going to be actually 15. So tomorrow's population is decreasing, actually, if you think about it. So we have 20 today at time 0, and time we got 1, and we have 15 here. So it's actually decreasing. And let's say tomorrow we come back, we go for 15. It's even decreasing even more. And then we have 7 here. So 2, we have a big decrease of 7. And then this goes on onwards. And you can see that eventually it will reach the bottom 0. So we're going to go something like this. It just kind of crashed down to this. So the entire population goes extinct in Adventure 3. So here's a comparison between Adventure 1 and 2. If we start from here or this area, whatever we do is that we're going to be pushed towards 100, right? This is our equilibrium point. And that's the interesting, that's the fascinating part about equilibrium point is that they will push to that side. And that's what we call a stable equilibrium. And the reason why I say call it a stable equilibrium, because look at Adventure 2, when we're kind of overshoots the 100, we're going to be above 100 for a little, it actually kind of pushes back to the same point 100. This is what the entire thing is doing. So that's why this is what we call a stable equilibrium. By the definition, the stable equilibrium is the solutions close to that equilibrium approaches that equilibrium. So basically you see from the left-hand side, from the right-hand side, both kind of merge into that single point. So that's why it's pretty stable. And in Adventure 3, we can understand that this point is what we call an unstable equilibrium. Because remember, the values from here just kind of push over to 100, right? It pushed away from A, and so is this one. You can see that it's gradually pushing towards 0. So despite it being in an equilibrium, every other solutions just kind of move away from it, right? So that's why A is what we call an unstable equilibrium. And so, yeah, this kind of mimics what real life scenario works, right? If we're lower than A, the entire population would actually crash to 0, becomes extinct. And now we can actually talk about the Cobweb technique because you guys have finally understand the idea and the fundamental logic behind that. So let's say, again, we start from 75, just like our previous example. This one, the Cobweb technique tells us that, okay, this one is going to go up anyways. So instead of doing that again over and again, you can just do a horizontal line. Okay, so we know that, remember, this one is 85, right? Then we know that here, the x value is also going to be 85. And why? Well, the reason being because this is y equals to x. We know that our y is 85. And this line, when we intercept it, it's going to be x. So x here is going to be 85. So now, it just becomes a lot more intuitive and easy if we can just go through this over and over again. And just like for the lower part, we're going to start at like 25. So 25 goes from here. We can just kind of go from here to here, down, 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 down. So we can see from the arrows that This also shows us where is our stable and unstable equilibrium. Obviously, in the middle, which is our A, it's unstable because we can see that the solution is being pushed away from both sides. So just a quick sum up, this is what I mean by Cobweb Technique, as well as what is an unstable and stable equilibrium. And because of time limit, this is just the part 1 of the video. I will be uploading part 2 and maybe even part 3. So much more we can dive into it. For example, where do you even get this graph from? Why is it curved like that? And what's going to happen after here? In some Cobweb techniques, instead of having this, we can see something like this. It's a downward spiral. What does that mean? So we're going to go through all that in our coming videos. So please stay tuned and enjoy. Thank you so much.